So for the first exercise, the first starting point was to define a path object with the dataset location. So data path, let's say dataset path, we instantiate with the string of the location where we have the data. And then we had to create a list with all the sessions that we had in the dataset. So in this dataset, as JC explained, we had like subjects, and for each subject we had multiple sessions. And so here we can say like to make a recursive search, so to search also in subfolders, we can say rglob for recursive global search. And the pattern that we can match for session is, for example, ses, and we can leave the asterisk so we don't filter for a specific number. And we had to create a list of this, and as we saw, this is not returning a list, this is returning an iterable object, generator, so we have to convert it to list if we want a list. And of course we have to first import path from pathlib. And yeah, this is all the sessions that we have in the dataset. And then we wanted to check the number of sessions that were labeled session 1. And I mean, this is not that different. We just have to refine our search to also specify the number of the session, something like this. And we can, at this point, just say length of this list, and this is 16. So we have 16 session 1s in this dataset. Okay, next question was finding the path of all the imaging data files that we had there. And this was also quite straightforward. In this case, what we have to match is the extension. So imaging data in these data sets are those data that have extension nii.gz. So we can just say asterisk. So we search any file name, and we just search with the extension .nii.gz. And this is the list of all the imaging data that we have in the folder. Then the next question was, okay, from this list, we can notice that there are different types of acquisition. So for some data set, we have, for example, here we have acquisition API. Is that pronounced correctly? Some acquisition are rare. And what we have to do is, okay, we have to start from this list, and we have to figure out all the different types of acquisitions that are around. And what we should rely on is the fact that the acquisition type is specified in the file name in between underscores, and is the second stuff, or like last one or second thing that we find separated by underscores. So we have some code, and then underscore, then the acquisition type, then underscore, then something else, and then the file name. So the trick here is to use, so we first create, like iterate over all the names of the files. So we say for path file path we iterate over all those file names, over all those file paths, and to actually have the name of the file, we use the .name attribute of the path object. And then now at this point, this is a string, so we can just split the string using the underscore. So we separate the parts of the list that are separated by underscore, and we take the second element, and we make a list with all those parts. Actually, let's do this in a list comprehension. So we can say acquisition types equal to, and we do a nice list comprehension, like this. We check out what we get. Okay. Oh no, wait. Oh, there was I missed one underscore, so it's the third element actually, sorry. Okay, so now we have the acquisition type for every single file that we get. If we want to find the unique elements in this list, we can simply convert it to a set, and this just gives us the unique values. Okay. And then, this looks like I was writing something and I forgot to finish. But yeah, we can create an imaging session data frame. Well, for example, let's make up this one. But for example, we can iterate over all the file path, and we can say, so we can create a data dictionary list. We start a list. So what I want to do is I want to create a data frame that describes this data set. I want to list over, I want to loop through all the files that we have. I want to parse information about the subject, the session, and the acquisition type. And I want to put it in a row of the column, in a row of the data frame under the right column. Since I start from a list from which I collect information, the strategy that I would use is I would create a list of dictionaries, and then I will create my data frame from a list of dictionaries. So let's start from the generation of just one data set for one dictionary for one data set before looping. So let's take the first file name. Let's say file name equal to the first element. So this is my file name. So let's just take .name, and let's just say .split underscore. And splitting the file name, I already have the number of the subject, the number of the session, and the acquisition type. Okay, and I would say let's keep those three informations. So we can say subject, session, type. I could write something like stuff I don't care here and make this assignment because I don't want to put this last part in the data in the data frame. Just for you to know, this is a nice interesting syntax. If you because the thing I cannot just do this, right? Because I am assigning 4 elements, so I need to put 4 variables on this side of the assignment. So this will complain. I have to put a 4th element, but to avoid assigning a variable that I don't care about, we can just use the underscore. Okay, so this is the convention for saying, okay, I won't care about what's coming in the 4th position here. This is actually a variable. It's just a variable with a name that you will never use in some reasonable code. So we are just tossing it out. Okay, so we can just say dictionary, subject equals subject, session equals session, acquisition type equal to acquisition type. Okay, and this is the data frame, the dictionary entry for one file. So this will be the content of one row of my data frame. So I just want to make a list of all those stuff for all the files. So starting from this code, I incrementally transpose this in a list by say for file name in. We are not assigning only one single element, but we are writing a full loop. We create a dictionary list that is at the beginning is empty, and then we append element after element, and finally we will have to import pandas as PD, and we can just say pd.dataframe, and we can pass to the data frame our list of dictionaries. And yeah, this is a nice data set of all the data frame that describes the content of our data set. Okay. Good. That was it for path. We will refresh them, revise them in one of the practicals today. So you will have the chance to have a look at them again, also if you were not here last lecture. But what I want to talk about today is a bit about images and imaging data and some common features that are, let's say, things that you have to consider about images, no matter what your imaging data come from, where your imaging data come from. This will not be strictly on plotting. I want to have one of the optional lectures that will start next week on plotting. I will actually send around this evening a poll on which lectures of the optional ones you would be interested in following, so we can decide which topics we will stick to. But yeah, I think that images are of good things to be aware of. Knowing a bit about images is not only good, having a bit of background of what images are is, I think, in general also good for, if you don't work strictly with imaging data, but just the fact that you have to generate figures, you might have to create figures for tasks or handle your own figures for a paper. In general, it's good to know what those, how those files look like when you look inside them. But yeah, even just taking to science, imaging data obviously pops out in a lot of different places. You can have just statistical images that you treat as anatomy that you treat using histology and anatomical images. You have functional imaging of any kind, where in your imaging data you also have information about brain activity. You can have videos that come from, you are tracking the behavior of a subject or an animal, and that's also an imaging data that you need somehow to analyze. But you all have to deal with images also if, for example, you are creating, you're working with any kind of visual task, and you have to generate such images. So yeah, the first starting point, which I guess most of you are aware of, is when we are working with any kind of images, we start from considering them not just as images that look like something, but actually as just matrices of numbers. And yeah, the idea is if you have an image, and in this case, this is a grayscale image, you have to imagine that every single pixel that composes the image as a value that is associated with that pixel that describes the intensity of the image at that given location. So an image consists of all those pixels and a number that in each pixel describe the intensity of the image. In this case, this is a grayscale image, so there's only black and white information, but there's this could be colored image, and so we would have information about colors on different channels. The most common formats we read images from are, I'd say, probably PNGs, which are usually two-dimensional and colored images. Do you have a question? No, sorry. Yeah, obviously stop me at any point. I also maybe for some of you, this is super boring. For some of you, I don't know. I hope this is not super boring for every one of you. But yeah, so PNG files are two-dimensional. When I say two-dimensional image, I mean a single image, not a stack. So not a video, not a volume of images, which can have color information and that are not compressed. So you don't have PNG files are very common because you don't have compression artifacts out of using PNG images. You as opposed to JPEGs, which I don't know if you ever tried to generate, but when you generate a JPEG, you specify an amount of compression, which makes JPEG as opposed to PNG a lossy compression format. So it is again a way of representing this kind of matrices of numbers. Yeah, obviously, efficiency is important because if you imagine the number of numbers that we have to keep for this image, The moment this start being a reasonably sized image, like I don't know, 180p image, this start be something like, let's say 1080 by 1080, like this is in the order of 1 million, and we obviously need some number of bits for each one of those pixels, so this can start easily become more and more megabytes, and we don't want our images to be huge. So each one of those formats, like PNG and JPEGs, they both find kind of smart ways of reducing the amount of information required to describe the full image. But the PNGs is like compress a bit less and make sure that we don't lose any information about the image, while the JPEG compresses more to the expense of losing part of information about the image. That is what generates the kind of funny artifacts that you see if you compress a JPG too much, which, yeah, probably in the fried memes you see a lot of those exaggerated artifacts that are similar to JPEG compression artifacts. As contrary to those formats that compress information, many times when you actually work with scientific data, two-dimensional scientific data, many times you use TIFF files, where in principle you could specify compression, but most of the times when we work with TIFF files, we do not specify any compression. So TIFF images in general will be larger than PNG or JPEG images that you're used to deal with. But yeah, you don't risk any, like you don't have any compression, so you don't risk ruining your data, losing information. And in TIFF files, you can also very easily create not just single images, but stacks of images. And we will see this, but you start needing a stack of images the moment you, for example, want to describe a volume, so where you don't just have a plane, but you have a full stack of planes in space that describe, for example, different depths in your imaging. Or you want to store, I don't know, a time lapse where you have an image that is acquired every some time. So yeah, that's the place where you use TIFF. We won't talk about movies like videos and video formats, but video formats like MP4 or AVI are basically more of the same in that they are like also capable of storing three-dimensional information, so frames across time. But they use, in that case, there is a lot of compression happening because, for example, MP4 is a format thought for storing like very long movies at very significant frame rates of very high quality images. So in that case, we have significant compression going on. So unless we are taking a video of a subject or an animal, we will never use MP4 for our data because MP4 comes with a lot of compression and lossy compression as JPEGs. There's also a bunch of other scientific imaging formats that you will be seeing, especially if you work with imaging data. This NRD or NII.gz, like the format that you were seeing in the exercise. There is OMIE.TIFF, which is a common format for microscopy data. But in general, there is like a whole zoo of imaging formats, many times, for example, specific for a company that sells you whatever device, whatever microscope, whatever stuff that is giving you images, and many times they develop maybe their own custom format that they also hopefully give you libraries to interact with. Okay, so it's difficult, like we cannot make a whole encompassing broad overview of any single piece of code that you can use for loading any kind of data, but all those libraries come with like a lot of online documentation, so you can just check it out. Yeah, here I'm just mentioning like the most important ones. So like if you have to start looking somewhere for some like library to start working with images, you don't have to start completely from scratch. This PIL library is what we will be using a bit today, and is very common if you have to work just with plain two-dimensional, potentially colored images. There is this TIFF file library, which is very common if you have to work with TIFF stacks. Image.io, which is kind of covering both, maybe. There is NI Bubble, which is a library that we will be using for dealing with the dataset that you downloaded. There is this other library which I'm mentioning, which is OpenCV, which in general I do not use for reading or writing images, but is very, very important if you want to start looking deeper into high performance image analysis. We will not cover this today because there's too many other things to talk about, but it's an important library if you need to process efficiently images. But yeah, in general, many of those classes you will find have object-oriented interfaces. So there is something that is common to most of those packages, the idea of if we want to read an image from the library, we will import a so-called image reader class. And then we will create a reader object from our file, and we will use methods of that object to read our images. Okay, and this is a consistent structure across several of those libraries. And yeah, to stick to one and start from somewhere and start having a look at actual data and images, let's have a look at this peel package, which I'm mentioning it now because you will have to install it for the practicals. Sometimes this is one of those rare, annoying, but unfortunately existing cases where if you want to install a package, you want to pip install something with a different name from the actual package. So this can be confusing, but don't worry. It's if you want to install it, you have to install Pillow. But the library itself is actually called Peel. And this just comes from, sometimes it happens that, some person develop a package and then they drop it and some other person start maintaining the package, but they cannot call it the same, they cannot make it pip installable under the same name because the guy already had is the proprietary of the online space where this name is used. And so you end up having basically a different name of the thing that you install, but nevertheless we import Peel when we work with this package. And for example, if we want to just have a look at a simple JPG image, which I don't know, I just put a JPG image in my folder, I can create to actually have a look at the image. I have to create an image object from the Peel library. So let's say from Peel library I import image. So image is my image class that I can use for reading files. And I can use the open method, and I pass the string that in this case this is a relative path, but could be the absolute path of the location where my image is stored. And this creates an image object. And if we can check out the type of image, and this is a JPEG image file object from the Peel library. Okay. Now, one nice thing about the Peel library is that looking at those images is very simple, because if we just write image as the last element of the notebook, this automatically just displays the image in all its glory. And so we can quickly have a look at what this is. Okay. In most cases, no matter what library you use, those image objects will have some data, and we'll get to that in a second. But they also have metadata, which, in some cases, for example, in this case, this is a simple just JPEG from the web, so I don't expect the metadata to be super interesting, but many times if your imaging is out of a acquisition device, out of a microscope, out of someplace meaningful, the metadata of the image, or the so-called header, is used to also store actual information about the data, where is the data from, what is the orientation, what is the resolution of the device that you're imaging it with, what is the brand, what is the version of the acquisition software, whatever. All those things are usually always kept into those image files together with the actual image data. Okay, and depending on the library, there are different ways of looking at metadata. In this case, there is just this .info, for example, method. But yeah, in this case, this is not super intriguing, because this is just specifying a bunch of information about how the JPEG compression was done. Okay. and we actually want to also look at the actual information of the image, like where the like let's manipulate the actual numbers that compose this this image matrix, right? And so one way, like the way I generally deal with it is I convert it to a NumPy array. And PIL images are super nice because they can directly be passed as the input to our friend NP-array function from NumPy. Okay, so this just, oh, I have to import NumPy. This just gives us a representation of this image that is now a NumPy array that I can play with. Okay, there's other, like, how we do this exactly can depend on the library. There are some libraries that have something like a get image data method that gives you the NumPy array. There can be different ways. And yeah, let's think about the size that we expect from this array. Okay, so anyone makes a guess about how many dimensions this data will have? So was this a grayscale image or a colored image? So, sorry?
No, nothing.
So if this was a grayscale image, it would be 2. Since this was a colored image, we have a third dimension that has 3 elements that are the values of each pixel across the RGB space. Okay. So yeah, in general, if an image is a plain 2-dimensional and monochromatic image, the data is a 2-dimensional matrix height and width. But we will have additional dimensions if we have a colored image. So we need, like, for an RGB image is just 3 values. Sometimes image can also have a transparency channel, like an alpha channel, which basically says whether, like, a pixel, there is a difference between a black or white and a transparent pixel, right? And the transparency in formats that supports transparency is encoded over a 4th element in the color dimension. And in those cases, you don't talk about RGB images, but RGBA images. We'll see. We'll come back to color spaces in a second. Additional dimensions can also encode the spatial depth. For example, if our data was volumetric, in that case we would get we would also need another dimension to represent the depth in space. We'll have a different image at every depth, and we can also have time axes, right? So we can have like frames one after the other that correspond to different time points. So if you want to encode, for example, a movie a movie that has colors, in that case, how many dimensions will you need?
4.
Yes. You will have, like, height, width, the color dimension, so 3 elements over the color dimension, and then the time dimension.
For grayscale images, is it still 3, like the triplet? I maybe missed it earlier, but monochromatic and grayscale are different, right?
I'm using right now. I'm using it. Yeah, you're probably monochromatic would be. I'm using it in the same with the same meaning.
Okay.
You of course can have, like, if you put the same value over all your color channels, you will have a gray image that is still 3-dimensional image, but is like it looks gray, but it's not encoded efficiently, right? Because you have 3 repetitions of exactly the same image for all 3 colors. Yeah, so in our case, we say that this is an RGB image, and so we expect the shape to be 3 of 3 elements, and the convention is the color dimension is the last one usually. I mean, as long as you know what you're working with, is not strictly necessary, but like usually that's the convention. Yeah, just to mention, because like this would be like a full lecture in its own, but like color spaces are like the notion of color space is the color space is a way of representing the color of an image. Okay. And there is like a lot of people have been studying what are the most efficient ways to encode the information about color. Most of the formats that encode color are actually based on triplets of numbers. Okay, so the most common one that we are used to is the RGB color scheme, where we have for each pixel we have 3 numbers that encode the intensity of red, green, and blue. Okay, and this is the standard basically for anything that we want to display on a screen. For professional printing, what is used is CIMeC, which is using 4 dimensions, and we have cyan, magenta, yellow, and black. So in this case, this is 4-dimensional space. Okay, we need 4 numbers for every pixel. There is there's people who have been developing a more kind of rational. Like, the annoying thing is like working with RGB. It's difficult to interpret. Like if you change one of the values of the RGB triplet, okay, you know that you are increasing the red or increasing the blue or increasing the green or whatever, but it's very difficult mentally to predict what is happening to your color. Okay, and if you want to create complex mappings of information into color, this can be very confusing. So people have been developed, and we will talk about this if we go into data visualization. But there is this other color space that you might hear, which is the HLS space, where basically 1 dimension is used to represent the color, is basically the position over the rainbow where we are. 1 dimension is used to encode the luminance, so the intensity of the white to black. Well, it's not strictly white, but the luminance of the pixel. And 1 axis is used to represent the saturation for that pixel. And you can imagine that like you can always convert an image in one of those formats into another one of those formats. It's just transformation. Like you can literally just move points, and you can map the same pixel with the same hue, exactly the same hue in any of those. But you will always need at least 3 dimensions to do this reasonably well. Okay. But yeah, most of the times we will be working with RGB images if we work on a computer, unless we want to generate something ourselves. So in our case, we can, for example, split the information about our image and plot separately the 3 channels that we had. So we had RGB. So here I'm just looping over the 3rd dimension, and I'm using imshow, the function imshow from Matplotlib, like not using it as a function but as an axis method, as we saw, to make subplots. And this is showing you the intensity of the image for each one of those channels. And yeah, the color obviously is, in this case, is entirely arbitrary, because in this case I'm representing just a 2-dimensional matrix using Matplotlib, and Matplotlib uses color map by default is this Viridis color map. So this is just the intensity over each channel of my image represented in this Viridis color map. Okay. What I can do with imshow is I can actually just imshow the full data array, and imshow knows that if I pass a 3-dimensional image with 3 elements over the last axis, this is reasonably encoding an RGB image, and that's why we can get it in color. Okay, so if you need to show an image in color, you can use imshow. Obviously it has to be 3 elements over the last, and by convention, the color dimension should be the last one. Okay. And yeah, we can see that there is red here and a lot of blue here. And if we go back, we can see that, yeah, there is more red over here and a lot of blue over there. So checks out. Okay, the other thing to notice is that when we deal with those images, so which are now matrices, the convention to describe the position of the pixels, okay, is the first dimension encodes the row. Like you literally have to imagine printing the matrix and assigning a color to every number that you see in the matrix, okay? And in matrices, we have shown that the first dimension is rows that are that goes from top to bottom, okay? And the second dimension is columns, and they go from left to right. So an image is described with the first dimension is high from top to bottom, and second dimension is left-right position of the pixel. And this might look reasonable if you come from the side of matrices, but this is horribly, horribly confusing if you think about what you're used to in terms of Cartesian coordinates. Like what we are usually taught in school, like when we work with like the standard Cartesian plane, XY plane, we always have our origin in the bottom left corner. And so we start from the bottom and we go up. And this might seem like not so relevant, but this can give a huge amount of problems if you have to like plot coordinates over an image, or you have to make up, like, the problem is this is flipping an axis. Okay, so if we actually look at how this looks like in the image coordinates representation, this axis is completely flipped compared to the Cartesian plane. And so, yeah, when we move at the intersection between the words of image and the word images and the words of coordinates, this can be super, super annoying, and you can expect a lot of confusions in terms of, like, because passing from one to the other literally flips the image. So if you if you take a contour in an image and you plot it, you get it flipped. So keep this in mind. There is no easy way around this. Like, this is Descartes made a mistake when he decided to go from bottom to top with his plane. There's nothing that we can do to fix it now. We have to stick with this inconsistency. Like, JC knows this is super annoying. Many headaches around this. But yeah, just be aware of the fact that there is this inconsistency. Yeah, very confusing. Another thing that I wanted to mention is the concept of bit depth. Okay, so as we saw, all images, like in images, we have those pixels, and those pixels are encoded by numbers. For those images not to become huge in size, we have to, like, because we have a lot of points, we have to think carefully about how many bits we need to encode the numbers that are in our image matrix, okay? Because otherwise, the imaging data can very easily explode, even for very small images, okay? And as we saw at the beginning of the course, we have this problem that, like, when we have to represent numbers with bits, we are limited in the number of numbers that we can encode, depending on how many bits we use to encode them. And obviously, the more bits we use, the heavier our data will be in memory. The term bit depth stands for how many bits, not bytes, bits I'm using to encode each number of my imaging data, okay? And the most classical value is 8. So normally RGB images, like the standard ones that you use, usually have values from 0 to 255, okay? Meaning that we have 255 possible values for each of the colors, actually. Sometimes, especially for scientific data, like data that you get out of a camera, will will many times, for example, be 60 bits, which gives you a bit more space to represent different values. Okay, and yeah, different file formats can support different bit depth or use one or the other by convention. And in our case, we can very easily know the bit depth of our image, because it will correspond to the D type of the NumPy array that is encoding the imaging, like the image data. Okay, so in this case, the D type is unsigned integer 8, which, if you remember a bit about NumPy types, means just numbers from 0 to 255. Okay, we can look at the image histogram, for example. The image histogram is the distribution of pixel values over the whole range of possible values that my bit depth is allowing me to span. Okay, so here I'm just to work with only one grayscale image. I'm just selecting the, let's say, the red channel. Okay, so I'm just assigning the red channel, and here I have to import matplotlib. So here I'm using the plt.hist function to calculate the histogram of my image, okay? And I'm just plotting it side by side with my actual image. And you can see, like, this is a reasonably looking histogram for my image. You can see we have values from 0 to 255. We have some values that are like just 0, but large majority of the values are distributed across my whole range of encoding. Okay. Beware of the fact that since the image has this UNIT type, we can only encode numbers up to 255. And this is the source of a very common artifact when you work with images. So if you take this image and you add an arbitrary value, let's say 100, okay, what happens is that since the type of this matrix allows only numbers up to 255, if the value of the pixels goes above 255, it starts from 0 again, okay? So if we do this sum here, and then we look at the histogram, we can see that the whole histogram has shifted, and then what was on that side entered back from 0. And this is the origin of those artifacts that sometimes, like, if you work with images, are like at the beginning they were for me are very common. It means that what are they meaning? Like, those were the pixels where you would expect the highest intensity, which now are completely dark because, like, we did not change the bit depth of the image, we just increased the number, and so these were misrepresented. Okay. So the only way around this, if we really need to change those values, is to first change the D type that we're using for the matrix. Okay. So in this case, I'm first changing the representation to unsigned integer 16. So now I have many more numbers to go, and then adding 100. And in this case, I get this result. So now I have an histogram that is perfectly fine and is going above 255. Consider that for doing something like this, I am just wasting memory, right? Because, like, I am just shifting the whole histogram. I'm not expanding it. Like, I'm not increasing the amount of information that I have. I'm just not using values from 0 to 100. And the price for this is I'm generating an array which is twice as big in memory. And if this was a small image, doesn't matter, but the moment they start being a large stack, for example, this can make the difference between fitting it in the RAM or not. So you have to, like, the moment you start working with those large volumes, you have to start being considerate about the bit depth of your image and how many numbers you need to encode. So you always need to keep, let's say, a balanced image histogram, okay? You have to be aware of how many bits you have, and you make sure that you use all of them. So, for example, a common problem that you can have, like, also if you just take pictures with your phone, sometimes the picture ends up being saturated. Okay, what does a saturated image means? This means that there are some points of the image where we are just seeing completely white, which are basically are too bright for the sensor to record them as different numbers. Like, we reach 255 on our sensor, and from that point onward, the sensor cannot disambiguate anymore between any value that is above that point. So if we look at the histogram of a saturated image, we will see that there is a large peak on this side of the image. And this is not something that we can fix in any way. Like the parts of the image that are saturated are parts of the image where we have completely lost information. Okay, so this being imaging data of any kind or a video of any kind, those parts of the image are wasted. On the opposite side, we can also have the problem of using not enough of our histogram to represent the image. So if you have for example, we are exposing very, very little, we can have only a few possible values because those are discrete values, those are not analog values, they're not continuous values. So in this case, I'm artificially creating an image where basically I only use values 0, 1, 2, and 3 probably. And we can see that like the artifact that I get in this case is I get very few different levels, and this is not of any advantage because I'm still using 8 bits for every single pixel. It's just that out of those 8 bits, I'm basically using for every pixel only 1 out of 4 possible values. Okay, so this is underusing the underfilling the histogram, and the other is overfilling the histogram. And yeah, the last thing that I wanted to mention in this section is this idea of binary images. So sometimes we want to create binary images, and this we can, like a binary image is just an image where instead of having a whole range of possible values for every pixel, we have simply true or false values. So this is an image that will be just black or white. And we do it many times, like we use many times binary images, for example, for creating masks, like for restrict our analysis to some parts of the image, okay? So if we just put, for example, a threshold on our data, we can create an image where we have 1, so true, only in correspondence to those voxels which were above that given threshold. And now we can use this image, for example, to perform masking operations on our imaging data. So, well, in this case, this is like not real three-dimensional data. The only information that we have in the third dimension is the color. But for example, we go back to the original image and just filter out the pixel. Like we can include we can make a new image which is completely black and is colored only in those pixels where the mask is 1, okay? And the way I do it is I'm just multiplying my image array times the binarized masks, and notice that I'm using I can do this operation with broadcasting. So I'm adding my binarized image is a two-dimensional image, right? Because we don't have color information. But we can add a color, a fake color channel, and then use broadcasting to perform this multiplication. And the result of this multiplication has values that are non-zero only where the mask is 1. And I mean, in this case, this is not useful, but if you add, for example, a functional, like a data which is functional imaging over time, and you want to restrict your analysis to a specific region, you can create a binary mask, and then you can do this multiplication, and then you can consider as signal only the stuff that is different than 0 because it was coming from the region that you're including in the analysis with this masking. Okay. Okay, so time for the first practical, which again, as last time, I would recommend to do locally. So you have to download the analysis, like the practical notebook, and run it through your local Python installation. Make sure you are logged in GitHub to download it, because otherwise it won't work.
just you keep the pillow installation.
Ah,
which
shoot.
is not a big deal.
Well, it will be relevant. Well, hopefully from the wiki.
Set this point.
If you're having issues with the installation, let me know. Don't waste huge amount of time. Se lo vuoi fare del notebook, in realtà c'è un trucco per farlo del notebook, che è metterci, se tu in una riga del notebook la cominci col punto esclamativo, lui lo prende come non come un comando di Python, ma come un comando di Ruby.
Ah, quindi io posso in teoria.
In teoria dovrebbe andare. Ma forse l'ho voluto farti installare con
Può essere.
Ma no, ma è abbastanza grazie della segnalazione, subito
import P from P import image. I was this index. So from P import image. I think that for that should include the field button. I will check it.
Thank you.
Um,